For today, we will discuss about metal oxide semiconductor transistors. Again, I'm Sir Febus from the School of EECE of Mapua University. So this is the structure of the MOS transistor. So we have 4 basic regions. You have the gate, then we have the drain and source, and then you have the P substrate, or this is what we call the bulk, transistor bulk or transistor body. Okay, so we have 4 terminals or 4 regions. Again, you have the drain region, you have the gate region, source region, and the bulk region, or in this structure drawing, that is the bulk or the body, or that is the substrate. Then between the semiconductor, so the P substrate together with the drain and source comprise the semiconductor layers. Then above the semiconductor layers, you have the insulator, which is actually made of silicon dioxide or simply the oxide layer. So that's the oxide layer. Okay, so N+, and the P substrate are the semiconductor layers. And then on top, you have the insulator, which is the silicon dioxide or simply the oxide layer. Then on top of the oxide, we have the metal layer. So gate terminal is originally metal layer, although it is improved and is currently changed into polysilicon material. So it is more stable in terms of thermal characteristics. So the gate layer is no longer really a metal layer, but it is now made of polysilicon layer. Although we are still retaining the name MOS. Is that clear? Please confirm.
Yes, po.
All right. So aside from the transistor regions, again, other important part of the structure, again, you have the insulator, or that is the gate oxide layer. So it electrically insulates the conductive gate to from your semiconductor layers. And then another important part is the channel. This is the semiconductor between the drain and source. So the channel is in this portion of the structure. So that is the material between the drain and source region. This is the cross-section view of the MOS structure, or the metal oxide semiconductor structure. Again, you have the drain terminal connected on the N+ region, source terminal connected on another N+ region. So this is actually an N-channel MOS device, or an NMOS device, or you can also call it as an N-channel MOSFET, metal oxide semiconductor field effect transistor. All right? So you have the drain and source. Then on top, you have the insulator gate, and then you have the conductive gate layer. Then at the bottom, we have the transistor bulk or body, which is the P substrate. In terms of the circuit symbol, this is how a MOS device in terms of schematic symbol looks like. So again, you have the gate and then drain and source. This is the basic symbol. So the substrate or the bulk is no longer indicated. So whenever you have a 3-terminal schematic symbol, the assumption is the substrate or the bulk is shorted or connected with the source terminal. So that would be the assumption. So drain, gate, and then source. And then as for the bulk, it is understood it is connected together with the source terminal. And also, I want you to notice that the gate terminal has a space or open circuit from the drain and source region. This indicates or signifies the insulation coming from the gate oxide layer. So the gate terminal is electrically insulated from the drain and source or from the semiconductor layers. All right? So when you apply voltage on the gate terminal, there will be zero current flowing from gate to the semiconductor layer. But instead, the applied voltage will introduce electric field effect. It will simply attract or repel charge carriers from the semiconductor layers. Again, is that clear? Please confirm.
Yes po.
Okay, thank you. In terms of dimensions, so these are the important dimensions in the MOS structure. The first one is the transistor length, or we also call it as device length or channel length. So that is symbolized by letter L, and it is typically in terms of micrometer or micron or nanometer. So the channel length is the spacing between the drain and the source diffusion regions. So that is what we refer as the transistor length. So in this example, transistor length is 90 nanometers. Another transistor dimension is the transistor width. Again, in terms of micrometer or nanometer. So W or transistor width pertains to the width of the source and drain diffusion regions. And another important dimension is the gate oxide thickness, denoted as TOX. This is the oxide thickness, and the typical unit is in terms of angstrom, or that is 1 angstrom, that is equivalent to 1 times 10 to the negative 10 of a meter. So in this example, the thickness of this oxide or the TOX is equal to 18 angstrom. All right, so is that clear?
Yes po.
Thank you. Now, how do we form channel? So as you can see in this structure, the channel between the source and drain diffusion region is initially not available. So the next question is, how do we form the channel? So let us discuss the formation of channel. So to do that, we have to apply a gate voltage. So apply a voltage source connected between the gate and ground. So that is denoted as VG, or that is the gate voltage. For this particular example, take note that the drain and the source are both connected to ground. So the only applied voltage is the gate voltage. So in terms of cross-section view, again, drain and source are connected to the ground, and the gate layer will be connected with the gate voltage VG. So once you apply a voltage, the polarity of that voltage will be distributed all throughout the conductive gate layer. So in this example, you have a positive connected to the gate layer. So a positive potential will be appearing all throughout the area of the conductive gate plate. And when that happens, the positive voltage will be attracting negative charges. It will attract electrons underneath the metallic or conductive gate layer. So take note, you have the insulation. So when you apply positive voltage on top, it will simply produce the electric field effect. It will be attracting negative electrons below the positive charge gate layer. So once we attract negative electrons underneath the gate region or the gate layer, then this area will be considered depleted. This area is originally, in this example, is originally a P-type material comprised majority by mainly by positive holes. So once you attract negative free electrons, the free electrons will recombine with the positive holes. So eventually, this area will become depleted as the attracted negative free electrons are recombined with the majority positive holes. And once we continue the attraction, eventually the layer underneath the gate terminal will have a high concentration of free electrons. So once we continue attracting negative free electrons, so eventually this layer will be converted from originally being a P channel, and then it will become neutral as the free electrons recombine with the positive holes. And as we continuously attract free electrons, the top layer will become negatively charged. So this area is actually effectively already an N-type layer. So this essentially connects the N plus source, then you have the N-type layer, and then you have the N-type drain. So that is why we refer to this layer as a channel. This is the layer or the portion in the transistor that will connect the drain and source and will allow the current to flow from the drain and source. So yun yung magiging daanan ng drain current natin. That's why we call it as the transistor channel. All right. Is that clear to everybody?
Yes po, sir.
All right, thank you. So take note that when the gate to source voltage or the VGS, so if you measure the voltage from gate to source, so that is the VGS. So when the applied voltage is equal to the threshold voltage, so we have a certain parameter, we call it as the threshold voltage. So when the gate source voltage VGS is equal to the threshold voltage, channel inversion happens. It means that the characteristic of this layer reverses. Originally from P-type, eventually it will become an N-type layer. So the channel characteristic reverses, or that is what we call channel inversion. And when that happens, it will effectively electrically connect the drain and the source regions. So again, this is the effect of the gate voltage on the drain current. So let us show the characteristic curve of the drain current versus the gate voltage. So this is our setup. So again, you have the gate voltage connected on the gate and the negative is on the ground. And at this point, we connect a drain voltage between the gate and ground, because previously, if we go back, even though we produce a channel, at this setup, there will still be zero current since the circuit connecting the drain and source region, there is no applied voltage source. So even though we already produce an N channel that connects the drain and the source region, since there is no applied voltage, so therefore the current will remain zero. Now for the next setup, we now connect a drain voltage such that when the gate voltage creates a channel connecting the drain and source, that would allow the flow of drain current, mainly produced by the drain voltage. All right, is that clear to everybody? Please confirm.
Yes, sir.
Opo.
All right, sige, thank you. So this is the characteristics. So when we apply gate voltage, the gate voltage must be above or greater than the threshold voltage. All right, before we can have drain current greater than 0. So in this particular setup, we will adjust the value of the gate voltage from 0 volt up to a certain value, and the drain voltage is set to a constant or to a certain value, and we are going to measure the amount of drain current flowing from the drain through the channel and out of the source. All right, so you'll have a circuit loop around the drain and source, and you have another circuit loop around the gate and source. All right. So when the gate voltage is less than the threshold voltage, the drain current is equal to 0. Now when the gate voltage becomes greater than the threshold voltage, we expect that the drain current will be more than 0. So when the gate voltage is equal to the threshold voltage, the drain current will still be considered equal to 0. All right, so it should be VG less than or equal to the threshold voltage. Okay, so note that when gate voltage VG increases, the drain current ID also increases. All right, is this clear to everybody?
Yes, sir.
All right, thank you. So let's have here the effect of the drain voltage on the drain current. So what if we set gate voltage to a certain value, and this time we adjust the value of the drain voltage and determine the resulting drain current. So from the characteristic curve, as we increase the drain voltage, we can see that the drain current increases linearly, exhibiting a characteristic similar to the resistor. So if you get the slope of this characteristic curve, this will give us the channel resistance or the turn-on resistance of the MOS transistor. All right, so in case you apply a higher gate voltage, so in this example, gate voltage 2, VG2 is larger than VG1, and gate voltage 3 is higher than gate voltage 2. So when we increase the value of the gate voltage, then it means you have a wider area of channel between the drain and source. And that would allow a higher value of drain current for a given drain voltage. So for example, if let's say at a drain voltage equal to this value, let's say VD equal to VX, the drain current when VG1 will be equal to this value of the drain current. When the gate voltage is increased to VG3, then the resulting drain current will be higher. All right, is this clear?
Yes, sir.
All right, thank you. So drain current ID, take note that the drain current of the MOS transistor is affected by the gate voltage as well as by the drain current. So the gate voltage is the input voltage that will that will produce the channel between the drain and source. But aside from the gate voltage, the drain voltage will also have an impact or effect on the value of the drain current. So from here, also remember that higher gate voltage would result to a higher density of electrons in the channel, and it will lower down the turn-on resistance and will result to a higher drain current. Now let's have here the effect of the device dimensions on the drain current. So from here, so transistor length, again, when you say transistor length, that is the distance between the drain and source regions. So you have here length 1, and this would be length number 2. So when the transistor length increases, as the transistor length increases, we expect that the drain current decreases. All right, so for a given gate voltage, the resulting drain current at a smaller transistor length would be this value for a smaller transistor length, and this will be the resulting amount of drain current for a corresponding larger transistor length. So as the length increases, expect that the drain current will decrease. Now, in terms of the oxide thickness, it says here that as the Tox increases, so in this example, this will be the oxide thickness. So that is the thickness of the oxide below the gate conductive plate. No? So from a smaller oxide thickness to a larger, up to this point, up to a thicker or a larger oxide thickness. All right, so again, for a given gate voltage, for a smaller Tox or oxide thickness, this will be the resulting drain current. And when the oxide thickness becomes larger, we can see that the resulting drain current becomes smaller. So Tox is inversely related with the drain current. As Tox increases, the drain current decreases. While for the transistor width, so this would be increasing width. So this would be a larger width as compared to a smaller width. So for example, for a given gate voltage, a larger transistor width results to a smaller drain current, while a smaller transistor width results to a higher drain current. So we can see that the transistor width increases and the resulting drain current will also increase. All right, so is this clear so far?
Yes, sir.
All right, so if you are later on to design your own, when you become engineers in semiconductor companies and you want to design a high power transistor. So when you say high power, it is a transistor that must be able to accommodate high drain current, higher drain current. So you have to design a transistor that would be smaller in terms of length, that would be thinner in terms of the oxide thickness, and that would be larger in terms of transistor width. All right? So again, you have here the MOS or the metal oxide semiconductor device size. Again, when you say transistor sizes, it pertains to the transistor length and transistor width. Now, when we use only the size, when you say transistor size, it would pertain to the aspect ratio, or it would pertain to the ratio of transistor width over the transistor length. So let's say, when you say given a transistor size of 10, that means when the transistor size is equal to 10, the transistor width will be 10 times larger compared to the transistor length. So for this particular example, perhaps the device size is around 1.5, no? Based on this, no, we can see that the transistor width is approximately 1.5 times larger compared to the transistor length. All right, so again, transistor size pertains to the ratio of width over length. Okay. Then as for the oxide thickness, take note that the thickness of gate oxide is fixed by the fabrication process. So this will depend on the fabrication company. This one will be determined by the designer, circuit designer. Okay, is this clear?
Yes po.
All right, sige, thank you. Now let us show the effect of the variation of voltage, or let us show the variation of voltage along the transistor channel. So for example, we apply gate voltage, and then the source is connected to the ground. So this will be the source, while the drain terminal is applied with the drain voltage. So again, the gate terminal has the gate voltage. So if you try to measure the voltage at the channel closer to the source region, then it would be gate voltage minus the source voltage, which is 0. So you can perhaps measure a voltage near the source region as equal to the gate voltage. And as we travel along the channel, since the channel will have a conducting resistance, we expect a voltage drop along the channel. So at the middle portion of the channel, we expect that the gate voltage, or that voltage along the channel, will be smaller than the applied gate voltage. And near the drain terminal, we expect that the potential difference would be gate voltage minus the drain voltage. So we expect that the voltage along the channel near the drain will become smallest. All right, so in this example, voltage here would be larger, and as we travel through the channel, we are expecting that the voltage drop becomes smaller and smaller as we near the drain terminal. All right, is this clear to everybody?
Yes po, sir.
All right, so ang concept dito, the voltage along the channel is not constant, no? Having said that, if this would be the distance along the channel. This will be the distance along the channel, and this will be the voltage along the channel. So at a distance equal to 0, going to a distance equal to the transistor length. So from the cross-section, it indicates that the drain current is flowing in this direction. So in semiconductor devices, the transistor channel is the dimension on which the device current is flowing. So that means we can consider that this is the transistor length at a distance equal to 0. And as we near the source region, as we go to the source region, we can say that is the distance equal to the transistor length. So at a channel near the drain, we expect that the voltage drop is minimum. So we expect that the voltage at 0 is minimum. And as we travel along the channel, we expect that the channel voltage will become the largest. In this example, equal to the gate voltage. All right, while on this you have VG minus the drain voltage. All right, is this clear to everybody?
Yes, sir.
All right, sige. Thank you. So we continue. Now, if we measure the voltage or the potential difference between the gate and substrate. So, ang measurement mo naman between the gate and the body or bulk. All right? So, in this example, at a channel length equal to 0, we expect, since the voltage drop here is minimum, so therefore the voltage from gate to the body will be ideally if BG minus BD is 0, so we can say that the voltage from gate to bulk will be maximum and will be equal to the gate voltage. And as we travel through the channel length, on this portion, the amount of voltage drop would be the gate voltage. So if you get the voltage drop in terms of gate and bulk, it would be gate voltage minus the voltage drop, or equal to the gate voltage. Then it would be equal to the gate voltage, or so it would be VD minus BG. VD minus VG. So it would be, so it means it is saying that the bulk has almost voltage equal to the drain voltage. So yun ang ibig sabihin natin dito. All right, is that clear to everybody?
Yes po.
Okay, thank you. All right, now again, knowing that the voltage along the channel is not uniform, but rather it is changing along the channel, then the amount of the electrons will also be not uniform. The channel formed will not be rectangular, but it is more of a trapezoidal in terms of shape. So if the voltage here is larger, then we expect to attract more number of free electrons. While if the voltage near the drain will be smaller, then we are expecting that the amount of electrons attracted here would be lesser. So if we distribute the electrons along the channel, we expect that the channel will be more of a trapezoidal in terms of electron distribution. All right, is this clear?
Yes, sir.
All right, thank you. Now, what if we further increase the drain voltage? If we further increase the drain voltage, then we expect that the amount of voltage near the drain would become even very, very small. So the number of electrons attracted would be minimum. All right, so it doesn't mean that the transistor channel is open circuit within this portion. It simply wants to highlight or emphasize that the channel near the drain would be very, very concentrated or would be very, very thin. But it will still be allowing the flow of the drain current. All right, is that clear?
Yes, po.
All right, you can imagine a garden water hose. Yung hose natin sa garden, no? If you turn on the faucet and hold your water hose at the end and try squeezing the end part of the water hose, so what will happen? So we are not completely shutting off the opening or the outlet of the water hose. We are simply exerting pressure at the end, and what will be the result in terms of the water current? Anong mangyari sa tubig kapag tiniga mo yung dulo? Di ba? Yung flow ng tubig mo mas malayo. Agree? Di ba? Mas lalayo yun, no? the rate of the current will become higher. The same with the MOS transistor. As we apply more pressure near the drain, this channel will become more concentrated. And it results actually to a higher drain current. Okay, is that clear?
Yes po.
All right. Okay. So another way to look at it is at the conductive gate, we are applying positive voltage. So we are supposed to attract negative free electrons under the conductive positive plate. On the source side, since it is connected to a ground, so the source will have the negative potential. So if you are the electron, what will be the response? This electron is more likely to be attracted towards the positive and it will be repelled by the negative. So most of the electrons will be moving towards this area. On the other hand, if you look at the drain region, the drain is applied also with positive potential, since you have positive drain voltage. So the electrons near this region has the tendency to be attracted towards the positive applied by the gate or towards the positive near the drain. So kumbaga nagkakaroon dyan ng counteraction, no? Between the positive potential applied by gate and the positive potential applied at the drain region. So that is why the number of electrons near this area would become lesser compared to the number of electrons near the source region. Okay, is that clear?
Yes, sir.
All right, thank you. So with that, let us have here the drain current along the channel. So if we want to determine how much is the resulting current flowing through the channel, so for a given area, we have the voltage along the channel with a dimension of x. So in this example, this is the channel length equal to 0, and this will be the channel length equal to L. So for a given cross-section, you have here the change in the channel length. So that is the x. And we try to measure the amount of voltage along that area. And we can determine the resulting drain current using the integral function. So determine the integral of the resulting drain current along the channel length dx from x equal to 0 up to x equal to the channel length L. All right? So if we process that function, that would result to this equation. So the amount of drain current flowing along the channel is equal to drain current ID equal to the mobility of carriers times the capacitance of the oxide layer multiplied by transistor width over the transistor length, all multiplied by the difference between the applied gate source voltage and the threshold voltage multiplied by the voltage between the drain and source, and then minus 1/2 of the square of the VDS. All right, is this clear?
Yes po.
Okay, thank you. Now, that would be the equation. So you have your ID equal to, ano yung formula natin kanina? Mu Cox multiplied by VGS, W over L, nalimutan natin, no? Mu Cox, W over L, multiplied by VGS minus the threshold voltage the difference multiplied by the VDS. All right, then minus or plus? Minus 1/2 VDS squared. All right, so from here you can say that the drain current is somehow linear with respect to the VDS. All right, so as the VDS increases, we are expecting that the drain current will increase linearly. All right, so ideally it should increase linearly up to a certain portion. And that is what we call the saturation point. So the saturation point is when the VDS becomes equal to the difference of VGS minus the VTH. All right, so when the VDS is equal to VGS minus VTH, the transistor will reach the saturation point. It means that the drain current will no longer be increasing, but ideally it will now remain constant. So starting from this point, ideally, the drain current will remain constant as defined by this equation. All right, so when VGS minus VTH, that is now equal to the VDS. So you have ID equal to 1/2 mu Cox W over L BDS squared, or BGS minus BTH squared. All right, so that would be the saturation point. And based on this equation, we can see that there is no longer a parameter pertaining to BDS. So even though you increase the BDS, the drain current is expected to become constant. Okay? So at saturation point, ID is equal to 1/2 times the mobility of carriers times the oxide capacitance multiplied by the transistor size, that is width over length, multiplied by the square of the saturation point, which is BGS minus VTH squared. Okay, again, is this clear?
Yes po.
Okay, thank you. So the region from BDS equal to 0 up to BDS equal to VGS minus VTH, this is the region we refer as the triode or the linear region. All right, you have the triode region or the linear region. And notice the formation of the channel. The channel is being modeled as somehow uniform from the source to the drain region. And as we reach the saturation point, starting from the saturation point, again, that is VGS minus VTH, we expect that the drain current will remain constant. So notice that the channel near the drain terminal becomes very, very concentrated. All right, so is this clear?
Yes po.
All right, so from BGS minus BTH onwards, this is the saturation region. So again, linear or triode region is when the VGS is more than the VTH and the VDS is less than the difference of VGS minus VTH. And we are going to use this equation. So you have the ID equal to this linear equation or linear model. And at saturation, VGS, again, is greater than the threshold, while the VDS must be greater or equal. So starting up to this value, this is the start of the saturation. So that is the saturation point. No? So when VDS is greater or equal to VGS minus VTH, then we are going to use this model or equation. Again, is this clear to everybody?
Yes po.
Okay, thank you. Now, let me introduce another concept exhibited by the MOS transistors. We have what we call the channel length modulation. If you look at the cross-section, when we apply higher drain voltage, we expect this region to become very, very concentrated or thin. And effectively, they are saying that the effective channel length decreases because of that, no? So you have here effectively a larger length. And once you apply a higher VDS, once we apply a higher drain source voltage, the effective transistor length becomes smaller. So the transistor length reduces. Alright, yan yung behavior exhibited by MOS or MOS transistor. Okay? So again, the saturation condition is the VGS must be greater than the threshold voltage, and the VDS must be greater or equal to the difference between VGS and VTH. And to take into consideration the channel length modulation effect, we are going to add this parameter. So lambda pertains to the channel length parameter. So this multiplier, this factor, will take into account the effect of the BDS. So ideally, we said that starting from the saturation point, the drain current is supposed to be constant. But based on the observations, as the VDS is being increased, it would result to a smaller effective channel length. And that would result to a higher drain current. So when the effective channel length decreases, the drain current increases. And that is reflected using this lambda, which is the channel length modulation parameter. And the effect causing, or the parameter causing the channel length modulation is accounted to the VDS. All right, is this clear?
Yes, sir.
Okay, sige, thank you. So normally I would write this kind of equation. So you have ID equal to 1/2. The mu Cox is the Kp. So Kp equals the product of mobility times the oxide capacitance. So you have Kp multiplied by W over length, W over L, multiplied by the square of the saturation point, BGS minus BTH, multiplied by the quantity 1 plus lambda, which is the channel length parameter, modulation parameter, multiplied by the VDS. So again, when you increase VDS, it would result to a lower effective channel length, and all right, please confirm if you can see again the slides.
Kita po, sir.
Okay, thank you. So again, when the VDS increases because of the lambda parameter, then the effective channel length decreases and the drain current increases. Okay? So as written, as VDS increases, the effective channel length decreases, causing the increase in the drain current. Another phenomenon exhibited by the physics or by the structure of the MOS transistor is the body effect. So body effect happens when the source and bulk have a different potential. So in this illustration, the source has a voltage, all right? And the bulk is connected to the ground. So if you measure the voltage between the source and bulk, in this particular example, then we have here a voltage VSB. That is the voltage between the source and bulk. As compared if the source is directly connected to ground. If source is grounded, bulk is also grounded, then the potential difference between the source and bulk will be equal to 0. All right? So if there is a voltage between the source and the bulk, then there is what we call body effect. Okay? So what is that? That is defined or described by this equation or model. The body potential, which is the BSB, will have an effect on the threshold voltage. All right? Defined by the body effect parameter gamma. Sir, paano ba nakuha yung parameter na yan? So the semiconductor manufacturer, what they will do is they will produce the actual transistor devices in the silicon wafers. And then afterwards, apply gate source voltage, drain source voltage, bulk source voltage on the actual MOS devices. So they will do the actual measurements. They will apply actual voltages and they will measure the actual resulting drain current. And then from there, they are going to extract. So from the measured values, they are going to extract the parameters. So dun lalabas yung KP, yung lambda, yung gamma, and in this example, yung P natin. Is that clear? Or do you have inquiries or question? Question? Is that clear? Please confirm.
Clear naman po.
All right. So dito naman in terms of attraction and repulsion of carriers, so in this example, gate is positive. And in case the source now also has a positive, so instead of attracting, let's say, 5 electrons or 6 electrons, one of the electron may be attracted towards the source kasi positive na rin yan. So that would reduce the amount of channel. And when you have a smaller region of channel, smaller area, then the resulting drain current will also be smaller. Naintindihan ba?
Yes
So if
po.
you want to
Yes, sir.
produce the same amount of channel, then you have to apply higher gate voltage. All right, and that is reflected on the threshold voltage. In order to turn on the device, because of the BSB, you have to apply an additional voltage. All right? So because of the voltage between the source and bulk, the resulting threshold voltage of the transistor increases. All right? So as the BSB increases, body effect says that the threshold voltage increases as well. Okay? So with this, these are the models or equations pertaining to the large signal or the DC characteristics of MOS transistors. So we have the linear or triode equation or model. We have the saturation model. And we also have the threshold voltage model. Okay? where ID is the drain current, VGS is the gate source voltage. Another circuit parameter, you have VDS, that is the drain source voltage. You have VSB, that is source to bulk voltage. Then W is the transistor width, and L is the transistor length. Then as for the transistor parameters, we have Kp, that is the transconductance parameter. VTO is the threshold voltage at BSB equal to 0. So when BSB is equal to 0, so it becomes square root of P minus square root of P. So the body effect is 0. So VTH would be equal to VTO. All right, so that is the threshold voltage equal to VTO. That is when VSB is equal to 0. Then you have lambda, that is the channel length modulation parameter. Gamma is the body effect parameter. And P is the voltage or the surface potential during the strong inversion when we already formed a channel under the gate layer. All right, are the equations clear to everybody? Please confirm.
Yes po, sir.
Yes po.
Okay, make sure to memorize this. So these are the equations that we are going to apply when we analyze CMOS amplifiers. So before we end, let me just mention CMOS technology. So when you hear CMOS technology, so first, CMOS pertains to a complementary metal oxide semiconductor technology. And it describes a circuit, it describes an integrated circuit that uses both N-channel MOS and a P-channel MOS. So whenever you have an integrated circuit or a chip using both the NMOS and the PMOS, that circuit can be described as a complementary MOS circuit or a CMOS circuit. Okay, is that clear?
Yes, sir.
Okay, thank you. So let me stop sharing. All right, again, these are the summary of the equations. Transistor current and voltages. So you have the drain current. So this will be the current flowing from the drain going out of the source. So for MOSFET, drain current is equal to the source current. All right? So the voltage at the drain will be denoted as drain voltage. Then this will be the gate voltage, that is the voltage from gate to ground. And we have the source voltage from source terminal to ground. Then you have the VGS, that is the voltage between the gate and source. Then we have the VDS, that is the voltage from the drain to the source. For the transistor parameters, we have VTO. Again, this is the threshold voltage when VSB is equal to 0. Gamma is the body effect parameter. Then what else? We have P, that is the potential at the surface of the channel during the strong inversion. And Kp is the transconductance parameter. And lambda is the channel length modulation parameter. So for the threshold voltage, to determine the threshold voltage, we are going to use this equation. So VTH is equal to VTO plus gamma, all multiplied by this. And cut off, so you have to determine first the threshold voltage. Then afterwards, we are going to compare the VGS with the threshold voltage. So when the VGS in the circuit is less than or even equal to the threshold voltage, we are going to consider the transistor being operated in the cutoff. And the drain current will automatically be considered as 0. Now, when the VGS is greater than the threshold, and we go to the other requirement, check whether the VDS is less than the difference of the BGS minus BTH. Check whether the VDS is less than the saturation point. So when these two are true, then the transistor is operating in the linear or in the triode region. And we are going to use this transistor equation. Then at saturation, when VGS is greater than the threshold and the VDS is equal or greater than the saturation point, that is the difference between BGS and the BTH, then the transistor, MOS transistor, is operating in the saturation condition. So we are going to use this equation. So you have 1/2 Kp W over L times the square of the saturation point, all multiplied by 1 plus lambda BDS. All right, so note that the BGS minus BTH is the BDS saturation point. And also note that for amplifier circuits, the transistor must be operated in the saturation condition. All right, is this clear? Please confirm.
Yes po.
Yes, sir.
All right, so I think for today we stop. Dito muna tayo, no?